that is also quantized. So he used that concept in terms of Planck's Planck's constant h. So as it is an angle part, automatically that 2 pi comes. That is the way it is nh by 2 pi is coming. Okay, so but later I don't know what was written in the NCERT, whatever the books you told, but it is possible to connect that also. By that way also h by p, if you consider mv and a substitute or cross multiply, you will get it in terms of what I will say, quantized one. Okay, nh by 2 pi, that is also possible, because this is just like later we will discuss that particle in 1D box. So this is just like a particle in a ring, so that 2 pi r come into picture. So that by that way, both way we can connect it. But when Bohr proposed that as a integral multiple, he didn't mean this de Broglie wavelength concept. Okay, de Broglie's concept. Just whatever the principle available that time. So again, exactly what it is written, that a book whatever you suggested, I didn't read that. So this is the answer to that question. With that I will go to the topic whatever we are discussing. This is what I was telling, this already discussed. And someone asked what about this k square and all. That is correct, as I told you, that you can take it as a constant, because this is the attraction towards the nucleus, so there will be a positive charge. I mean, in principle, that electron is attracted towards the nucleus, so the nucleus charge will be there. So depending upon books, different details would have given. And moreover, sign there is no significance, because they are opposite. So we are just equating that force towards that. So we discussed up to the radius, I guess. Otherwise, this is the expression. So we are starting from here. Once again, I will go quickly. So E square by R square is equal to mv square by R. That equation. So we are equating those two forces, balancing forces. From that, we can write V square by equating this. And angular momentum is quantized nh by 2 pi. So mvr is equal to nh by 2 pi. From this, we can get the expression for V. And again, you take its V square and equate these two equations 1 and 2. And by simplifying, we will get the radius of an orbit of quantum number here. So this is the way how it is derived. And the energy, we can also calculate the energy of an electron in an orbit. Energy of an electron in an orbit, you know that total energy we can write as a sum of kinetic energy and potential energy. This you have to remember for all the cases. We will be discussing several models in quantum mechanics. So there we have to, the total energy is always the sum of kinetic energy and potential energy. These are simple things, so I want to go a little bit fast so that I can compensate the last lecture. But this is very simple. So you know that a total energy is the sum of, moreover, this is recorded, so you can go through that lecture once it is over if you have, if you face any difficulties. Okay, E equal to half mv square, that kinetic energy equation, that you know how kinetic energy is calculated, and potential energy, that is E square by R, that is attracted to attraction towards that nucleus when you write. So we can write, as we already have the equations for V square as equal to E square by mr from the previous slide. And if you substitute for V square is equal to E square by mr, so substitute here for V square, so that m and m will cancel, and you will get E square by 2r minus the second term as such. Then if you subtract this one, you will get minus E square by 2r, minus E square by 2r. Okay, so this we got the expression for E, and now you know what to do, because we have already the expression for R from the previous slide. You substitute. If you substitute, we will get the energy as minus 2 pi square m e to the power of 4 divided by n square h square. Again, it is quantized. So nothing, very simple. We wrote the expression for kinetic energy, total energy, and substituted for V from previous slide, a previous result, and substitute, and again R you substitute, you will get this. So from here you can see that depending upon that value of En, you can see that negative value will be more. if depending upon the value, if n is very high value, this will be a very small value, and if it is very small value, then that denominator will be a very high value. Accordingly, you can have the energies of various orbitals depending upon the quantum number here. Okay, so like that, if you substitute for n equal to 1 and n equal to 2, you can see how it is just an expression. And why I'm writing is we will be going for the difference between these two levels, very 11th standard textbook points only. So if you subtract E2 minus E1, we will get, you can take the common factors outside, so you will get this expression. And depending upon that value of n1 and n2, we will have we can calculate the energy released or energy absorbed for that. This is just various expression for energy, E2 minus E1, so that difference E, we are writing it in terms of frequency, and you can, whatever the unit you want, either wave frequency or energy or wave number or whatever that you can convert it into proper substitution. And finally, we will have this expression. And once you substitute this constant values, whatever it is, then we can get that energy difference E2 minus E1 in terms of that wave number, that is equal to 1 by n1 square minus 1 by n2 square. All these are values. If you substitute, you will get a constant called Rydberg constant. Okay, by this way you can calculate the energy difference. Once again, this is first chapter of your 11th. And you know from where to where it is going, whether it is coming back from n2 to n1 or n3 to, in principle, from any level to any level, it can change, either excite or it can come back, de-excite. Okay, depending upon that, energy will be released, or if it is going up, it needs the energy. Okay, so this is if you substitute those values and all, you will see that this comes under various series in the spectral line, and in which region it appears, that is also given. That all these are known facts. Now, what that means, Bohr's explanation could explain a lot of things. It gave a very clear picture about atom. I don't know whether it is clear or not, but at least it was very, even now we are using that concept as such to explain many of the chemical phenomena. For example, the first reaction, whatever we studied, that is, I don't know whether you call it as a reaction or not. The first one of them is Na and Cl. Na 281, then Cl 287. So one needs one electron and one has a lack of electrons to complete the octet. So Na will give Na plus and Cl will give Cl minus. Very clear picture about an atom. But later, maybe after 1 or 2 classes, you will see that that picture of atom is not as clear as we think. That means initially we had nothing. That means when you are studying your 5th, 6th, 7th standard, there was no idea about atom. Idea means, okay, you know what is an atom, what is an element, what is a molecule, what is a compound, everything. But slowly you are getting into that. Then you had some clear picture about atom, as I told now, sodium, sodium, chlorine, so Na plus ion, Cl minus ion, why it is a 281, or why it wants to become Na plus, so that octet will be completed. So very good clear picture. These electrons were moving around a circular orbit, everything is okay. But later in this course, after 1 or 2 lectures, we will see that the picture of atom is not as clear or as we think. How do we know that? Later, there were, with the advances in the theory as well as in the experiment, mainly because of the experiments, it was found that Bohr was not correct in some cases, although it gives a very good picture. So limitations of Bohr, where Bohr model failed. Bohr model could not explain the spectra of many electron systems. Okay, hydrogen-like system, it was okay, but as more and more electrons are there in a system, when you take its spectra, there were some complications. There were something unexpected coming. Okay, that is possible only with the advances in experiments also. Also, it could not explain the Zeeman effect or Stark effect. You know what is Zeeman effect and what is Stark effect. That is very interesting. You think about 100 years of before. Nowadays, we have all kinds of equipments, but still we are not able to assess or analyze anything. But that time, most of the things, they were analyzing the results. They were keep on thinking what to do next and all. I'm not denying that there is no such experiments today. Really, there are experiments, but 100 years of before, how they did, how they thought, how they analyzed their results, these are even now the fundamentals of most of the things. Okay, so we have to see the things in that point of view. And moreover, it could not explain the fine structure of hydrogen atom. Fine structure means splitting. Okay, one line, whatever we expect, that is okay. But why it is splitting again? That is again possible only if we can go through that much resolution. Otherwise, you will not see that. Okay, so we, even that time they could observe that. That means the techniques were very good at that time also. That is why they could explain all those things. So many places Bohr model fail. Okay, then that de Broglie hypothesis, again the details of de Broglie is given here. I heard that the thesis, PhD thesis of de Broglie was only pages. Exact number I don't know. Even nowadays we are writing papers. One paper, after doing our research, we submit papers of pages. And sometimes as a supplementary information we provide instead of giving all the details in the paper. But the entire thesis of de Broglie was only few pages. If I remember, somewhere in between 5 or 28. Exactly, I don't remember exactly. So very few pages thesis, PhD thesis. So that is his contribution on this. So you know the concept of matter waves was matter waves or de Broglie waves. Okay, though according to that, for any matter we can associate a wave corresponding to that. However, that wavelength, comparing to that wavelength, it is not that much significant, and it is not discussed most of the times, especially for macroscopic particles. But still we can talk about that. But if you go to the smaller particles, this is very important. That wavelength is considerable. We have to consider. And that is what he suggested. That means they have both particle nature and wave nature, which was not known that time. Okay, so later, although it was mentioned for electron, later not only for electrons, for some other systems also, very small particles also, it was discussed, or experiments have proven that it is possible. For example, even here you can see that not only for electron, not fundamental particles, even for atoms and small molecules, this is true. Through various experiments it was proved. Okay, so the idea of de Broglie is that this is just like a story, is that it has both types of nature, both wave nature and the particle nature. And then Heisenberg's uncertainty principle, there are a lot of interesting things, and we use that main concept, that is wave particle duality of microscopic particles imposes a limit on our ability to measure the position and momentum simultaneously and precisely, because we cannot determine that. If you try to determine that position very accurately, then that will have some effect on its momentum. That means without, I mean, if you to detect that, you have to disturb. When you disturb, that will have its own effect. Okay, the more precisely we determine the position, the less accurate is our determination on momentum. Or if you try to look at its momentum, then it will affect its position and vice versa. Okay, so this is expressed in terms of an equation, delta x into delta px in the order of Planck's constant. And more on uncertainty principle we will come later. Okay, this we will have to discuss later sometimes. And historical background, when I discuss, I have to go a little bit back also. This Planck's Max Planck contribution equal to h nu about the black body radiation, and also Einstein's. There are several works, but one only made up light as a packet of photons. And that second part, that means the light in the packet of photons, that is, we can say that that is just like a particle nature of electrons, and the best experiment to prove that is the photoelectric effect. You are aware of what is photoelectric effect, and it is also demonstrated here using a picture. So if electromagnetic radiations of suitable frequency or energy falls on metal surface, then electrons are ejected. 1 second, please. Because I'm in a class, I will call you back if it is not urgent. Okay. I'm in a class. If it is not urgent, I will call you back later. Okay. Sorry. So photon of energy h nu, when strikes on a metal surface, part of the absorbed photon energy is used to overcome the forces holding the electron in the metal, because that electron is tightly bind to the metal. So some energy is required to eject an electron. But if you are giving more energy, the rest of the energy, whatever it wants to come out of that metal surface, then that will be converted to its kinetic energy. So a minimum energy is required. After that, the rest of the energy of that photon will be converted to the kinetic energy. So all these things are known to you. So if you increase the frequency, of light, then the energy of the photon will be increased. You know that h nu, if frequency is more, then energy will be more. So after that, whatever it is required to eject from the metal surface, the rest will be converted to kinetic energy. So if you hit that with a high energetic radiations, the kinetic energy of the ejected electron will be more. But on the other hand, if the intensity is more, then more and more electron will be ejected from the surface. Okay, now that is fine. Now next is, again we are going back to an electron. So what is an electron? We discussed that it's a particle nature here, and there are some other experiments to show the wave nature also, although I have not discussed explicitly here. So there are two nature. Then still we ask, we know this principle, we studied everything and all, but if I ask you to close your eyes and ask what is an electron, I don't know what you will be feeling, but most of the people, including me, no doubt at all, I can consider think about electron as minute, but wave I cannot accept, because that I cannot, because human minds or brain is not to accept something as a wave. Okay, so we cannot feel that. So you can, what is an electron? If I ask, maybe we can tell, okay, this is just a very too exaggerated picture. Okay, whether it you know that from this it is showing a particle and this as a wave, because we represent by using the waves as a curves and all. But it is okay. But actually, what is an electron? Neither this nor that. We know something else, but we always prefer. If I ask you to think about an electron, automatically that particle nature only comes into your mind. But that is fine. This is what this is the directly I took from Levine's quantum chemistry book. An accurate pictorial description of an electron's behavior is impossible using the wave or the particle concept of classical physics. We cannot say that. The concept of classical physics have been developed from experience in the macroscopic phenomena. That is okay. that is acceptable. If you are talking about in something about planet motion and all, that is fine. Planetary motion and all, it is fine. But what about the minute thing that even we cannot see? Then the human nervous system is not developed to deal with phenomena at the atomic and molecular level. So it is not surprising if we cannot fully understand such phenomena. This is just like taking an anticipatory bail, because later in the some lecture sometimes students lose its interest, but that time don't stop it. I have something for those students. That is the one thing I can do to make you interested, so that you have to attend. Don't miss a single lecture, especially for this particular part, quantum mechanics and group theory, because this lecture is just to fill the gap. Others can just read it. Please,
Sir,
yes, please.
sir, if a particle is a collection of waves and a waves is a collection of particles, sir, then why are we calling waves as waves and particles as particles?
You are telling superposition.
No. I am telling that whatever we call particle is a collection, maybe a collection of small waves, and whatever we call waves may be a collection of particles. Sir, so then the particle wave thing should not like exist. No, like why are we terming everything?
Terming means I didn't get.
Sir, whatever we are terming, like we
terms you are telling. I heard it as a TURN, so I didn't get it. No, this is just we can interpret just like our philosophy kind of things. We can think whatever we want. This is just to use why we are doing all these things, to explain certain phenomena, to understand something and all. So whatever the way it is convenient to you, whatever we can explain the experimental facts, we can go with that. I'm not sticking neither with particle nor with waves. I'm not asking you have to think about particle, not able to waves also. Depending upon the whatever you can explain, you can use at the way you like. For example, if something is helping us to considering, for most of the time that is the thing. For example, chemistry point of view, if you talk something sodium Na plus and Cl minus, I'm not terming as you have to go with this particular ways. If you can accept that, that is okay, but most of us cannot imagine or accept that. For example, later I will each and every time when we tell something, it is always good to correct ourselves. I will tell the situations where it comes. So here I'm neither telling it as a particle or a wave, but whatever the way you want, you can consider and think about that as far as it explains, if we can explain some of the facts. So here, why I told these things, yeah, quantum chemistry things. So here, why we are, I don't know, you are answered, you got your answer or not. But what I'm saying is that it doesn't matter the way you are. I was coming to that point. For example, we were talking about sodium ion. There we will always prefer to think electron as a particle, because that helped me to understand the chemical reaction. Okay, sodium atom, one electron is given or it is lost, so that I have an Na plus ion. Similarly, Cl minus is taking that electron. So in that case, to understand that chemical reaction, that particle nature really helped me. If it doesn't matter if electron is a particle and moving from the sodium to chlorine or chlorine to electron, for that to understand that chemical phenomenon, it was perfectly okay. There was no problem at all. But if I tell that electron is a wave and ask tell the student that you see sodium, it's one of the wave is going to the Cl minus, not wave. Again, I'm not completely correct with that. I mean, sentences I'm using, words I'm using, but still, okay, you see one electron wave is moving from here to there, then chlorine that is taking one electron wave has reached, then always that student or human beings will have a difficulty to understand. Sometimes we will have to take it as such so that it will help us to learn many things. Later you can correct yourself. That is what I am telling. So I'm not telling that electron is a particle or electron is a wave or whatever the way you, that is up to you. But certain things to explain to make the people understanding, it is better to take it that particle nature and sometimes to explain that wave nature. So I'm not telling that electron is a particle or electron is a wave. I will leave it to you. It has both character and all. But the idea is that depending upon if it helps to learn you a lot, I'm just taking that. At the same time, if I tell somewhere that electron is a particle, that time it helps to me to explain these things. But at the same time, you can correct yourself. I mean, when I am telling, I will correct. I always correct myself. No, that is not a particle, like that. Similarly, wave also. This will require later. For example, one example in advance I am telling. For example, we call it as electron. What is that? Plus spin, minus spin, alpha spin, beta spin, clockwise, anti-clockwise, up, down. What else? Plus, minus. But you know that these are nothing. Actually, that are two different states, spin states. But to explain that, to explain bonding and everything, we use all these type of terminologies. So if it is helping to understand something better, we are using that. After that, you can correct yourself. So when I say electron up, down, actually nothing like that. Clockwise rotation, anti-clockwise rotation, nothing. These are two states only. But when I say two different spins in that way, it is easy to understand and I can explain that chemical or physical phenomenon better. So in that case, I use it. At the same time, I correct myself. No, electron, nothing like that. So that you can practice. That is what I was telling. Because most of the time, certain things, if you accept, that will help us to learn many other things. Later, you can correct it. Okay, for example, this is one story I still remember. One of my own teacher asked, for example, when we were small kids, our parents or grandparents, teachers, whoever maybe, they used to tell some stories. In those stories, these animals used to talk with each other. But that time we never asked, oh, they cannot speak, how, blah, 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 like that. If we keep on asking such questions, we would not have learned most of the things. But later, now you know. Now, if I tell that this fox told that lion, then you may question. But it helped you to learn many things, just like that part only. Okay. Again, I should not go. Away from that topic. So again, I'm not terming it as a wave or particle. Just both as. But the idea is that our human brain is such that we cannot imagine electron as a wave. The reason is that we are used to with this materialistic world. Okay, then at the most what you can do is you can consider electron as small as this, or even smaller than this. But still our brain is just like to consider as a particle, but if you can correct at the same moment, that will be really great. Now, that is why if quantum mechanics feels something difficult to you, nothing to worry, but everything will be okay now. For example, as I told now, that Bohr picture of atom was very clear, but later what will happen? Wait and see. Okay, Bohr picture very clear. Two electrons are revolving here and around the nucleus. Very good picture. Then where we lost that, we will wait and see. Okay, so the real journey starts now. That is why I was little bit hurry, because I thought that I will stop in the last lecture here. Unfortunately, I could not. Okay, now we will start the real journey of quantum mechanics. What it is. The first one itself starts with the postulates of quantum mechanics. First itself postulates. Some postulates are there in quantum mechanics. Okay, so what are those postulates? you have to be listen. I will not say that you have to understand each and every slide now. I have some other slides to make you understand, but you have to listen. Let me start with the first postulates of quantum mechanics. What is the first postulate of quantum mechanics? This is for all, irrespective of physics, chemical engineering, those who want to change the branch, it doesn't matter. Just a simple postulate of quantum mechanics. What it is, the state of a system can be expressed as a function of position and time. Once again, the state of a system can be expressed as a function of position and time. I don't know how many of you got something from this statement. Honestly speaking, when I read this first time, when I was attending my first lecture, I did not get anything from this postulate. The state of too philosophical or abstract, not philosophical, abstract. The state of a system can be expressed as a function of position and time. You see, this is the first postulate of quantum mechanics. If it is introduced to a student, this statement, simple words, but altogether it is a very complicated sentence statement. So if there is not, the reason why students are getting away from quantum mechanics is just the first postulate is itself like that. Now, let us read it again, that what it is telling. The state of a system, I am repeating that again and again. The state of a system can be expressed as a function of position and time. This is just like that. In when I was doing my high school, we had a social sciences, we had politics. Not the politics whatever we have, politics and economics, two parts of social studies other than history, geography and all. I don't know whether you have studied or not. Oh God, it is too complicated. Each and every sentences in that book was connected to each other at the same time, no connection at all, that kind of statements. One of the subject I really, I could not go through that topic at all in the entire subject, politics. So this is, for some students, it is just like that. The statement is too complicated, but there is something very interesting. If you look at it very closely, let us try to understand it in a simple way. The state of a system can be expressed as a function of position and time, and it is represented, the state function or wave function of a system. I am not telling what are these systems. In general, I am telling the state function or the wave function of a system is represented by the symbol psi of xt. Psi of xt. It is telling that psi is a function of position and time, a wave function. Okay, this statement, third statement, is very important about the first postulate of quantum mechanics. What it is? The more we get the information about position and time, the more accurate the properties predicted. It is very important. If you know the wave function, we can predict the properties of the system. Once again, I am repeating, if you know the wave function of a system, whatever be the system can be anything, an electron, an atom, a molecule, maybe yourself, a material, maybe yourself, whatever it may be, system in general. So the more we get information about the position and time, the more accurate the properties predicted. That means if you know the wave function of a system, you can predict the properties of that system. Again, if you know the wave function of a system, we can predict the properties of the system. But the problem is that how you will get to know that you should know the position at different times. So it is telling that if you know the system at position of a system at a different time, you can predict the properties. I'm coming into the language that you can understand, not the exact language. Principle is more or less the same. Now, with this, you read that statement again. The state of a system can be expressed as a function of position and time. Now I think at least you are familiar with the statement and you know what it means to some extent, not completely.
Sir,
I will come back.
what is
Yes.
what is
Sorry?
the state?
State
State
means how it looks. How, I mean, that is again that how, what I will say. I don't know what to tell that the state of a system, how the more details about the system, the how the system behaves. I didn't mean that liquid state, solid state, gaseous state, nothing like that. The property of a system. Let us say take it like that. The property of a system like that. 1 second, please. I am in a class. I will call you back once it is over. So that maybe we can consider that how the properties of the system is or how it looks like, anything. The state can be anything. More details about that system. That's all.
Sir, I had a doubt. Can I?
Yes, please.
Sir, when we are saying that the state of a system can be represented as a position, as a function,
that is just a representation only. We are using psi as a function.
And when we talk about an electron, so by Heisenberg's uncertainty principle, we say that we cannot calculate appropriately the velocity and the position of the electron simultaneously. Then we are saying that we cannot simultaneously precept the position and that time simultaneously for an electron. That is why we talk about the probability distribution function. That
yes.
That is the reason. Okay.
Yes. Because we cannot exactly. So we will go to that probability from here. So this is just like a, I mean, I'm happy that you asked and you got the answer and you explained for all also. That is very good. But again, I'm telling, maybe you would have read something or thought about that. This is just I'm introducing as a nursery class kind of first lecture. Okay, nothing, blank paper may. Sirf, I am just introducing that wave function, but anyway, it is good that you already got that point and all. But again, I am going back as if we are starting from the scratch. From a blank paper, I am just writing. That's only. Okay. So the state of system, the state of a system. You see, now I will prefer to answer later. Otherwise, I cannot even. I mean, I have to think about the peak of the Gaussian distribution. Okay, last question, please, sir. Please,
yes, please. Sir, I was saying that, yes, sir. Sir, if there does this statement means that electron at different position and different time will have different properties if we consider that as a system.
That is true, actually, that is true. But I don't want that whatever you are telling is correct. You know that if the electron is in the 1s orbital, that is not the energy it has when it is in the 2s orbital. Okay. So whatever you are telling is correct, but again, my system is nothing. System, I didn't even talk about electron. Electron is an example that you can apply here. For me, the system is a system, any system. So I have not even come to the electron. But whatever you are telling is correct. We will come back to that. We will come back to that soon. Okay.
Okay, sir.
So that is why even I did not write anywhere system. That is, I already told you system. I'm not telling my system is an electron. I'm not telling my system is an atom. I'm not telling my system is an molecule. I'm not telling my system is a material. That is why system in general I'm telling. Okay, you have only this answer you will get. I'm very happy that you are asking with those questions, but at the same, let me move little bit. Okay. You will get the answer to all of your question, but you are absolutely correct. The electron, the same thing, whatever you told. Okay, so again, once again, forget about all the discussions for the beginners or those who never thought about those things. For them, I am telling any system. I'm again, no electron, no atom, no molecule, any system I can talk about that properties, predict the properties if I know the position and time. Now, information from position and time, then you may think, oh, how important is this position and time? That is very, very important. Position and time is very important, not only for an electron or an atom. We will see with a simple example. Once again, those who have difficulties still, the state of a system can be expressed as a function of position and time. The more the details you have the position and the time, I guarantee that I can predict the properties. For that statement, I will explain you a simple example. You see, there are two things you can see on the slide, left side and right side, position and time. OK, now I will go through some time and some position. Let us see and let us try to predict something. You can see two places, two different places and two different time. 2nd October 2021, 8 o'clock. I hope you know the importance of this day.
Yes, sir.
Okay.
Yeah.
Now,
Yes,
next another time, and you can see the position. You can guess something. I will not tell anything. You can guess something, and something is happening in one place, and something else is happening in the other place. So you have position and time. So my idea is just to tell that how important is position and with respect to that whether you can predict something or not. Now you know the importance of the day. Many of you already told, although I didn't listen to you, I'm sorry, but you know the importance of the day. And now, right now, I'm again new time. Position right now I cannot tell, but at least to some extent I will tell that attending CYN 001 at IIT Roorkee. Right? Right?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir.
Now you see with that position I am predicting the other side. Okay, so you see with the position and time I could predict. But a prediction may not be complete because my information is not correct. If I go further, maybe I can reach up to each and every one of you by updating the position and the time. If I update it, okay, and again, if I keep on updating the things, I can even predict what it will be or where you will be after 10 years. But I have to update more and more details on position and time I need. Even after IIT reaching IIT Roorkee, that is not enough. Maybe I can predict one of you somewhere in Stanford after 5 years. That depends, but I need more information. This is a very exaggerated one, but just you will never forget the importance of position and the time in this one. That is my suggestion. So just like this is one side one and this is another side. Two different wave function or state function. Okay, this is very exaggerated, I know, but just to tell you that how important the position and time to predict the properties. Now you read your first postulates again. The state of a system can be expressed as a function of position and time. So again, system, we can change the system, can be anything, electron or blah, blah, blah like that. And even like you yourself. But the prediction may not be correct because of various other reasons that will come back. So that is why the third sentence is very important. The more information about the position and time, the more accurate are the properties predicted. Now, okay, that was an exaggerated system. That is fine. Now let us go to one thing. Now you are going to predict. I will not predict. You will be predicting something else related to that first postulate of quantum mechanics. Let us correlate the position of electrons, okay, with the properties. Now you have two pictures, left side and right side. Just have a look on left and right, and you may have something would have come to your mind right now, right? I don't know what it is, but I'm sure that by looking these two pictures, definitely something would have come to your mind now. Now you know that R is different for these two cases. Now the first one, you are predicting the atom is in its excited state, right? By looking that you are predicting, right? Compared to the first one, the second one is in the excited state. So you see, yes, by looking the position, by looking the positions, you predicted. Now the system is unstable. You again predicted. You see, compared to the first one, you can tell now that the second one is unstable. Why? You know that if the energy is more, system will be unstable. Now, that is one. Now you can predict about one more thing. It may, as it is unstable, definitely it will come back to the ground state. So when it is coming to the ground state, what will happen? It will emit the electromagnetic radiation, and it will emit the electromagnetic radiation. Then if you know these two positions exactly, you can calculate the difference and you can predict the energy difference. Then you can convert to the lambda at which it will be emitting. All these things are clear. So you see, you predicted. That is what I was telling. Okay. But there is a problem. What is that? The problem is the wave function psi of xt has no physical meaning. You see, there is no physical meaning for the wave function as such. Wave function is giving all these. Using the wave function, we can predict the properties, but the wave function as such, no physical meaning for that. Then if now there is another kind of what it is really, no doubt at all. I am telling wave function is the God, everything, but at the same time I am telling that that is not, that has no meaning at all. Then what to do? There is that second postulate 2. That is what Born postulate. It is also known as Born postulate. What it is telling, maybe you would have heard about this, or in some other words, not in the form of a postulate of quantum mechanics, but the key concept maybe you are aware of. What is that? If the wave function of a system has the value psi at some point x, somewhere, if you know the wave function psi at a particular point x, then the probability of finding it between x and x plus dx can be obtained by squaring that wave function. That means, although psi has no value, if you take it to square, that gives some information that is very valuable. For example, if the wave function for x, this is a psi square dx one dimensional, but if you are taking a 3-dimensional, you have to take dx, dy, dz, so that we use as d tau, volume element. Okay, so what it is telling is that although psi has no meaning, its square tells the probability of finding. Its square gives the probability of finding in a definite space. If it is a volume element, that will give. So its square is very important. Square gives something to us. Square gives some physical. We can interpret that result with the square, but not the wave function as such. Next, these are some numerical problems point of view, and you have to note it because psi square and psi square dx, that how we term it as, that is a different. Psi is called the probability amplitude, psi square is the probability density, and psi square dx is the actual probability. Okay, so in principle, we will have to integrate it later. So you need this volume element also. If it is a one-dimensional, then it is fine dx. So just for these three are we call these three as a different, not the same. This is probability amplitude, that has no meaning, but psi square we take its probability density, and if you really want to get the actual probability, you have to integrate over that space. That is the second probability. And for a complex wave function, the probability is psi square psi d tau. The reason is that what is meant by complex wave function? You are aware of complex numbers. So if you square a complex number, you will get an imaginary number. Probability cannot be negative. Probability is either 0 or positive probability. 0 is okay, otherwise some positive, but not a negative. Okay, that is why psi we are taking it's the conjugate. This is a mathematical convenience only. Okay, so psi square psi, otherwise psi square d tau. Sorry, psi conjugate psi or psi square d tau. If it is a real wave function, no problem. Otherwise, we have to take the complex conjugate of that. So although psi has no meaning, its square is very important. That is about the second postulate. That I already told you because probability cannot be negative. Now, this is a mathematical technique. Yes, please. Jaldi.
So what was the importance of the last line?
Importance of?
Last line, that complex function thing. Why is a complex function?
Complex functions, you will see that some depending upon the properties of the system, sometimes the wave function can be complex also. We will discuss about the wave functions later. So this I am telling you. Sorry.
So some probability.
In that case, the probability will be if your function is complex, then when you take it to square, complex means I will come na iota. So then if you take it, that will square will give negative. So probability, we cannot consider it as a negative probability, either 0 or positive. That is why we take it. Sorry.
Complex multiplications are not always real. They are complex many a times.
No. You are multiplying that wave function and it's a complex conjugate, so that it will be real.
Okay.
No, both are not. One. That is why psi conjugate. It is not a multiplication. You please. I'm sorry. I don't know whether you. It is confusing or not. This is psi conjugate psi, not psi into psi. Okay. So we are taking the conjugate of that wave function so that you will not get the negative number.
The square of modulus of psi.
Yeah, but I can write. Yeah, you are correct. Okay, yeah, you are correct. So here this is a mathematical treatment. We have to use it later, but this is the right time to talk about that. So I am just writing normalization of a wave function because there are certain conditions for a wave, how a function should be to acceptable wave function that we will be discussing later. So this normalization of a wave function is a mathematical technique. We do it from -infinity to +infinity unless it is restricted for a particular region. In that case, we will be writing the limits for that. Then psi conjugate psi dx is equal to 1. This is the normalization. If that wave function is satisfying this condition, we can tell that that is a normalized wave function. Just remember this one. There are some other special slide for you. Those who gets some lot of queries, concerns on this particular equation and all. For the time being, you just have a look. I will say that only. Okay, just have a look at this. We will come back to this later. We will come back the requirement of this equations sometimes later. For the time being, just I am telling that a wave function can be normalized by this method. Then the question is how to normalize a wave function. Okay, why a normalization to be how a wave function to be normalized, that we will see later. And later, now the reason is that how to do that. Okay, whatever it may be, how to do that. For that, I am giving just an example. For example, if you want to normalize a wave function psi of x, how to do that? What you have to do is that instead of psi of x, you consider the wave function as n into psi of x. That means multiply with a constant with that psi. Okay, then you substitute here. That means instead of psi, if your wave function is not normalized, you consider a constant multiplied with this one. So n into psi and n into psi star will come. Okay, so then that n you take outside. There are two n, one from here and one from here. Then n square it is. So that n square you take outside and you this n square, the value of n square you can find out because by integrating this you will get a value. That value with n square should be 1. From that you can find out the value of n. And once you know the value of n, substitute it back to your wave function. Then your n of psi is a normalized wave function. This is a mathematical steps procedure I told. With an example, it will be very clear to you. So again, if the wave function is not normalized, you can normalize it by considering your wave function as a normalized one by multiplying with the n. Then substitute your normalization condition. So both n and n will come outside. That is a constant n square into this integral part. Integral part will give you a number. N square into that number should be 1. Then from that you can calculate the value of n and substitute back to your n. Then n psi of x is your normalized wave function. With an example, it will be clear. For example, if I give you the equation. Yes, please.
What is n?
N is a normalization constant. A constant. Any value, just a constant and substituting, and I will get that value. We will do that in the next slide. So for example, if you want to normalize the function exponential minus alpha x square by 2 within the limit minus infinity to plus infinity. Suppose you want to normalize this wave function psi of x. That is as I told you, this is a wave function. So I'm using exponential minus alpha x square by 2. Then if I want to normalize it, as I told you, instead of psi, you take it n psi. So n square will be out. So n square into minus infinity to plus infinity psi conjugate psi. This is not a multiplication conjugate, but in this case it is a real function, nothing to worry about that. So if you substitute here, that equation will be n square into e to the power of minus alpha x square by 2 into its conjugate again e to the power of minus alpha x square by 2 dx is equal to 1. Now you know these are exponential alpha minus alpha x square by 2 into e to the power of minus alpha x square by 2. You can use your mathematics will tell that it is e to the power of minus alpha x square dx, right? Product. Again we have n square. Now we have n square into integral minus infinity to plus infinity, and you know that this is a symmetric function. So I can write this instead of minus infinity to plus infinity. I can write it 2 times 0 to infinity. One from positive 0 to plus infinity and another one 0 to minus infinity. As it is a symmetric function, I can write it as 0 to infinity. Why I am writing? There is a purpose for that. Why I am writing? Anybody knows? Can comment? Why I am doing that instead of minus infinity to plus infinity?
And the even function.
Yes, it is an even function. That is why I am using. Why I wrote it as 0 to infinity is this is a standard integral. So 0 to infinity 2 times I wrote because this is a that is why 2, because this is a standard integral, and you know the value of the standard integral is this one. So I know this function. So my idea was to convert this into this one so that I can substitute this value here. So if I substitute here 2n square, this integral value as I mentioned on the right, this was this one multiplied, that should be equal to 1. And if you do that or simplify that, you will get the value of n as this. Now your wave function is psi of x is equal to this into this. This is a constant, as I told you, this is a constant that times of your wave function. This is a normalized wave function. Okay, so this I just showed you one example for how to normalize a wave function. How to normalize a wave function I showed you. The reason is that we will have to normalize several wave functions in this course. So this is just a technique I showed you how to normalize a function. We will be normalizing several functions later. Now it is those who wants they can leave.
Sir, till now we have
there are many things to discuss, but that we will come discuss it in the next class. Yeah, please.
So till now we have been
you can have.
Till now we have been taught that e to the power minus alpha x square dx is not integrable.
Yes, sir. I have to read that.
Yes, sir.
Yeah, that is why I'm using this normalization part thing also, because we have to get as a there are certain conditions for a wave functions to be acceptable wave function. So in that case you will have to use a normalization constant. So this is a technique for those things whatever we will be doing later.
And sir, I wanted to ask you one other thing, that during the starting of the class I didn't get any link and I was not able to join this class also. So please can you add? Please can you add?
How did you join then? How did you join then?
Sir, someone my friend invited me.
Okay. Then you tell me your mail ID. Why you are a new student or?
No sir, I have attended your previous class.
No, class is a different thing. All of you have to remember one thing. Many of you may be attending class. It doesn't mean that you are a registered student. So later there will be a problem for your examination. So it is your responsibility to check your academic portal and your name appears there or not. Very important. You don't miss any mails.